Hello, hello, hello. Welcome to this. This is, I have a bit of a cold, so just bear with me. And if you don't understand anything, just tell me and I'll repeat it, or I'll go slower. So if you can't hear me or you don't understand me, just put your hand up and I'll try again. So everyone's talking about neural networks. If you... I'll shout. So that's better. Everyone's talking about neural networks. So this talk really is about what everyone's talking about. So it might be a bit basic for you if you already understand neural networks, in which case feel free to help me out. Otherwise, I'm going to start at the beginning. So first of all, what exactly are we trying to work out? There are two rough classes of problem. One is regression. So regression means you're trying to find a continuous output. So like the price of a house or something like that. And classification means you're trying to choose what class an output belongs to. So maybe you're trying to work out if something is a cat or not a cat or a dog or what type of image something is. And in regression, you're looking at house prices. So first of all, what we're doing with neural networks is trying to work something out. And the way that neural networks kind of come across as magic sometimes, or they did to me when I started out. Like they could solve any problem. But really, in a basic way, neural networks are just glorified function machines. So we're trying to map some inputs to an output. So we might be trying to map like the size of a house and the number of bedrooms to how much the house costs. Or might be trying to map all of these input pixels to work out, is it a cat or a dog? So first of all, what's a neuron? So neurons have been thought to have been the fundamental unit of the brain and the nervous system. They're responsible for receiving and processing input from the world and sending commands to muscles. And we have about 86 billion neurons. If you do any research on the internet, you might see this figure, 100 billion neurons, quite a lot. But just as an interesting side story, this scientist, Dr. Susanna Herculano Huzel, melted down 4 adult male brains into like brain soup and tried to count some of the neurons and scale up. So she actually found that we have about 86 billion neurons. And that's kind of interesting because this discrepancy of 14 billion neurons is roughly the size of a baboon brain. So there we go. So signal outputs from a neuron can excite or inhibit other neurons. If a certain threshold is exceeded, the neuron fires. And the more a neuron is excited, the more frequently it fires. And they release neurotransmitters, which are these chemicals. So if you imagine a neuron getting excited, and the signal travels down the axon into the terminals here, and then these chemicals are released across this synaptic cleft into the dendrites of a receiving neuron. But the really important thing, and the reason why I'm telling you this, is that these synapses can adapt. So they can alter the amount of chemicals that they release, and they can alter the amount of chemicals that they receive. And this might seem a bit boring, and it's not really anything to do with programming, but it is, and we'll get there, I promise. So neurons work together, and the brain is modular. And the connections between the neurons can adapt. But why are we talking about neurons in the first place? Well, in 1906, these two men won the Nobel Prize for Medicine and Physiology. I'm going to try really badly to pronounce their names, and I have to apologize to everyone when I do. But interestingly, they hated each other. So let me just make sure I've got the names the right way around before I tell you this. Golgi invented a technique to look at neurons in the brain using silver nitrate. And both Kajal and Golgi drew pictures of the neurons that they saw when they did this. And Kajal's view, or Cajal, if I'm trying to pronounce it correctly, was that the correct level to look at when we're trying to understand the brain is the individual neuron. And this became known as the Neuron Doctrine. So the whole reason that we're looking at neurons and we're talking about neural networks can be mapped back to this theory that that's the level we should look at. Other theories might be that maybe you should look at groups or you should look at different muscles, but this is the Neuron Doctrine. And this became pervasive throughout machine learning. So in 1943, McCulloch and Pitts wrote this really important paper. It's more correctly attributed to McCulloch, but what they noticed, and it's really important, is that property I was telling you about neurons firing, is that they either fire or they don't fire. So there isn't an in-between. They're on or they're off. And so they linked that firing to logic. And so the idea that you can build logic gates in neural networks and these binary threshold neurons comes back to this theory. So next we had perceptrons, which are a really early model of neural networks by Rosenblatt. They're actually still used in some systems by Google, and they have some really interesting properties, but they don't have the same learning potential that we expect from neural networks now. Because what we want from our artificial neurons is the same ability that the brain has to adapt and learn. So unfortunately for Rosenblatt, in 1969, Minsky and Papert wrote this book, Perceptrons, which is about all of the problems with perceptrons and why they couldn't learn. And then for a while, neural networks were kind of devastated because people thought that there were such big limitations they weren't worth looking into. And we had this big period where people weren't doing a lot of research and it dwindled. So, often called the godfather of deep learning, if anyone's interested, Geoffrey Hinton from the University of Toronto. In 1986, this paper came out about a learning procedure. And even though the learning procedure already existed and it was actually invented by a few different people at the same time, this suddenly sparked an explosion of interest because after finding out that perceptrons didn't work, these guys came along and said, actually, there is a way to train these networks and it's effective. And then, with greater computational capacity, suddenly we have this explosion of interest in neural networks. But not everybody agrees that the individual neuron is the correct level to look at when we're trying to understand the brain. So that's just a bit of history for you, that when we look at neural networks, we're looking, it's not a theory of the brain in the way that a neuroscientist or a cognitive scientist would understand. So you can't look at artificial neural networks in their basic forms or little networks and think that's how the brain works, because a lot of people who know more about how the brain works will really disagree with you. But nonetheless, it's an exciting field and people are very excited about it. Now, there are two interesting branches of research in neural networks. One is trying to get a better understanding of the brain from looking at neural networks. And if you're interested in that, watch this TED Talk. This is Henry Macram of the, again, I'm sorry for pronunciation, from the University of Lausanne, leading the Blue Brain Project, which is well worth watching and looking into if you can. And the other branch of research is trying to understand a style of parallel computation that is really roughly based on this understanding of the brain, or the Neuron Doctrine and the theory that we can map these logical functions by artificial neurons. So, back to what we're trying to work out. I mentioned regression and classification. So, the idea that we're looking for a continuous output, like the price of a house, or we're looking for a category. And what we really want from neural networks, and what we're really trying to achieve, is we want them to be able to do things that we find easy. So computers at the moment are really good at working out something like this. And if you got the answer straight away, shout it out. I wouldn't know if you were right or not. I have no idea what the answer is. But it'll take you less than a second to work out what this is, unless you've never seen a rabbit before. So we want our neural networks to be able to look at that image and know that it's a rabbit. And that's the challenge. So from now on, when I talk about neurons, I'm going to use the term neuron to refer to an artificial one. So now we're switching. We're going to leave the biology behind, and we're going to just look at artificial neurons. So what is an artificial neuron? First of all, let's just look at this function. So imagine X is some kind of input feature. Don't get put off by the symbols, by the way. So imagine X is like the size of a house, like 100 square feet. And what we want to know is what the price of that house is. So maybe we have to transform that. Maybe the price is like 100,000 euros or dollars or whatever, and the size in square feet is 100. So obviously we have to do some kind of multiplication. And then maybe we've got a bias term. I'll talk about that in a second. So a linear neuron really is just mapping these inputs to some kind of output. And that little W there stands for weight, because that's what we're going to multiply the input by. So you can think of it as weighting the input. It's either going to make it bigger or smaller. So here's an example. We might maybe we want to times the input by 2. And we want to add 2. So there are our inputs, and that's our weight, and that's what we're going to get out of it. And it's just a linear function. So it's the equation of a straight line. And that bias term, the B there, is just like the y-intercept. So let's draw it like this instead. Let's pretend this is an input neuron, and this is another input neuron, and this is the neuron they're feeding into. So remember we had that axon traveling down. They're the values traveling down, and that's going to fire. And that weight is the synapse adapting. So remember, the synapse can alter how much goes in and how much goes out. We might have more inputs, and then it gets slightly more complicated. Actually, no, sorry. It doesn't get more complicated. It's just like scaling up. So maybe that sum in the middle there, that question mark, is just the sum of all of those inputs. And you might see that written in a few different ways if you look at the literature. So that symbol there just means sum. So maybe it's just all of those things added up. I'm just going to go back to the last slide and show you that. So what we'd have is that input times that weight, plus that input times that weight, plus that input times that weight, and that's your answer. And just a reminder, that weight represents the synapse. So the bigger the weight, the bigger the input. The smaller the weight, the smaller the input. Now, if you've got your laptop in front of you, just go to this website here. I'm going to bring it up and show you. And this just gives you something to play with. So I was talking about a linear neuron. Don't worry about what these other things mean right now, because I'll go over them. And what this is trying to do here is it's trying to separate 2 bits of data. So it is a classification problem. We want to know if the data belongs to the blue set or the orange set. And if we try and run this with a linear neuron, what you'll find is that it doesn't successfully separate the data. And the reason for this is that that's a non-linear function. I'm just going to stop that, otherwise it'll go forever. Now, I'll show you a little example, and I have to apologize because the example's in Python, so just don't read the code, just pretend it's Java. So what we might be trying to do here is map some kind of function like a straight line to this data. So we can see here that it's done quite badly. And what we really want is we want a line to run through that data. So let's just change this value here. Not that code. Okay, so that's better. So all we're trying to do with that linear neuron is just map some kind of function like this. So it looks really simple. We're just trying to draw a straight line. So that's what we were looking for in the TensorFlow example. So the problem with that linear neuron is that we're not really getting anything. We're just mapping a linear function. Is everyone following me so far? I'm going to take the one nod as a yes. So we can't really get very much from that, and you might be thinking, where are we going? So let's look at the binary threshold neuron. So McCulloch and Pitts, who I told you about the 1943 paper, came up with this idea of a binary threshold neuron, and this is based on their logical idea that a neuron either fires or it doesn't. It either outputs something or it doesn't. So what we're looking at now is from the linear neuron, we had all of these inputs summed together, and now we want some kind of concept of it activating, or like the neuron firing. So we apply this threshold function, and what it means is if the sum of all of the input is above some kind of value, then fire, otherwise don't. So it's either on or it's off. So that goes back to that idea that we've got these logic gates almost. So let's now have a look at logistic. This is what really took off. They're not used so much anymore, but back to this idea of something firing. So if you do neural networks and you do, say, Andrew Ng's course on Coursera on machine learning, you'll hear about the sigmoid function. And this is where it gets more interesting, because now we can map things to non-linear outputs. So now we've got this function, which should look like an S. I'm just bad at drawing. And it goes to 0 or to 1, depending on the size of the input. And that's interesting because now we can solve that problem where we're trying to separate the two dots. So if you play with that again, you should see it working. More recently, there are some more neuron models, like rectified linear neurons. And these are all basically different functions mapping the outputs. So have a play with those. But what we're really interested in is the difference between the output and what we should get, because we're trying to predict something. So imagine we have the size of a house in square feet, and we have the price. When we feed that through and we've got that weight function, we want a way of getting the right weight. So we want to know exactly how the input maps the output. We want to know what makes a cat and what makes a dog a dog. So what we're trying to do is we're trying to learn these weights. And that's the crucial thing. So in order to learn the weights, we need to know what the difference is between the right answer and what we've predicted the answer to be. So we have these things called loss functions. And you might see them called cost functions, like the cost of it being wrong, or the error function. How wrong is my prediction? So we're trying to work out what makes a cat a cat. If you feed something through a network and it's really wrong, then you know you've done really badly. And you have a way to measure it, you can see if it's getting better or worse. And what we really want from all of these little neurons and these little function machines is a way of getting a good prediction. And so to get a good prediction, we need a way of measuring it. So for a linear neuron, it might be the squared difference. Don't worry about the maths, because if you do anything on TensorFlow or deep learning for J, you actually don't need to know this. But just if anyone's interested, we might be looking at the difference between the predicted output and the actual output, and the average of that. Just if anyone's interested, there's the equation for the sigmoid neuron, but I'm not going to go into it. So now we have our neurons, and you might still be thinking, okay, so how am I going to work out if a cat's a cat or a dog's a dog from one neuron mapping something? And you're not. The real power comes in chaining them together. And one of the reasons that deep neural networks have really taken off is that people have found the bigger the network, in most cases, the more accuracy you get with these really deep neural networks. And that works by chaining these neurons together. So we might have an input layer. And if you're trying to input a picture, how would you do that? Okay, so what you might do is you might take every pixel and flatten it out in one big array of pixels. And if it's grayscale, just have a value for the percentage grayscale. Or maybe if you want to do red, blue, green, then you'd have 3 different values for each. And you want to feed them all into this input layer. And then what happens is you do this multiplication with the weights. In literature, you might see W, or you might see a little Greek symbol for theta. And then we work through the network, basically doing those single calculations where we're adding up all the input, putting it through a function, outputting it. But we can do that again and again and again and again. And the reason for that is we can map more complicated functions. In neural networks, you have this concept of a hidden layer. And it's called a hidden layer. If you watch anything by Geoffrey Hinton, apparently they called it a hidden layer because it sounded cool. But some people say it's called a hidden layer because you don't directly control what goes into it. You know the input layer, you know the output layer, you don't necessarily know the hidden layer if it's a big network. So when we move through a network, from the point of view of what is actually happening at each step, we feed in the data to the input layer. And then we do these multiplications. And then in each of these neurons, so if you just imagine going back to the individual example, times that by that, times that by that, times that by that, add it up, activate it. And we do that for each of those. And then we have some more weights, and again, these are the synapses controlling the input and the output. And we go to the next layer, and we get our output, and we have this hypothesis. The hypothesis is the predicted value. So the crucial thing, the really important thing in all of this, is getting those weights, the theta values or the W's. And so we want to know these mappings. So we have our error. Remember I said the loss function or the cost function. So the discrepancy between what the network said the answer is and what we know it should be. So now we have a way of knowing how wrong it is. And there are different ways to work that out, as I showed you the 2 different equations. And now we have this concept of the cost, or the error, or the loss. And we have the weight. And what we want to know, looking back at that network, is how every one of those weights affects the output. Because we want to get to a place where the cost is lowest for the weight. So for every one of those, we want to get to the bottom of that curve. There. And that's where the concept of backpropagation comes in. So the Geoffrey Hinton paper in 1986 and other authors. Backpropagation is the idea that we've got this output, like the house of a price. We know what the answer should be, and now we need to change each of those weight values to work out how we can get the predicted answer as close as possible to the real answer. And so you can imagine, because we're trying to minimize that error, they're actually trying to walk down a hill. Trying to walk down a hill to get to the lowest point, the point where the weights are such that we have this really tiny discrepancy between the real answer and what it should be. And that's easy in 1 dimension because we're just going down in 2 dimensions because we're just going to the bottom of that curve on the graph. In 3 dimensions, it's more difficult because you're trying to walk through a landscape. So in 10 dimensions, it's really difficult. And in 100,000 dimensions, it might seem impossible. And that's where algorithms like gradient descent come in, because we're trying to get to this minimum point to reduce the weights, to change the weights to such a point that the cost is reduced. But you don't have to implement that yourself, unless you're really keen. There are lots of libraries that do that for you. So if you look at Tensorflow and you go on that example, you don't see any of the maths behind it. But now maybe you know a bit about why it's working or how it's working. So let's go back to the Tensorflow example. I'm going to change that to the sigmoid neuron and just show you it converging here. Eventually, if you just keep watching. This thing here called the learning rate. If you remember, we're trying to walk down the hill in this landscape to get to a point where the discrepancy between the output and the real answer is the smallest it can possibly be. The learning rate is like the step size. So you could take a massive step. So imagine you're a giant in a hilly landscape. If you take a massive step, you'll completely overshoot the valley and you won't get to the lowest point. And if you're tiny, when you take tiny steps, it's going to take you forever. So the learning rate is how big a step you take each time. And that's a really important thing to configure, because if it is too large, you can completely miss it. If it's too small, like maybe this is a bit too small, you'll be waiting a long time. Okay, so if you start playing with neural networks, you might come across this problem called underfitting. And what happens is your prediction is too simple for the data. So if you imagine you have your house price example, and actually it turns out that the price of houses compared to the size works something like a curve, but your network just outputs a line. And so it can't get the complexity of how the data is changing. And so that's underfitting. So maybe your network is too simple. If you remember back to that diagram with the different configurations, or again, if we look at TensorFlow, you might not have enough hidden units here. And remember, for really complex functions, we need more hidden units or hidden layers. So you might need to change that configuration. And the really difficult thing about neural networks isn't necessarily understanding all of this, it's learning how to configure them. Another thing, as we saw with the linear neuron, is your activation function might be too simple. If it's just a straight line, you're not going to learn to fit it to a complex curve or a circle or anything like that. The opposite problem is overfitting. So maybe you fit your data so well that it doesn't generalize to anything new. So one example is, in the early works with AI, they were trying to train a neural network to tell the difference between Soviet and American tanks. So they fed in thousands of pictures of tanks. And it learned to distinguish between the pictures, the Soviet tanks and the American tanks. But then when they took a new picture, it didn't get the right answer, and everyone was confused. And eventually they realized that all of the pictures of Soviet tanks were taken on a cloudy day. So what the network learned was to tell the difference between a cloudy day and not a cloudy day. So we need to be able to generalize to new examples. If you fit your data too well, then one way to do it is not to train on all of the data. So imagine you've got details for 100 cancer patients on the tumor, and you want to work out if it's malignant or benign. And so what you do is you hold back some data, you train your network and you run it through on, say, 60% of your data, and you test your hyperparameters, like the number of hidden values, hidden layers, hidden units, the learning rate, and you try that on 20%, and then you do a final test on another 20%. Otherwise, there's something called regularisation. So, is anyone familiar with principal component analysis or dimensionality reduction? Okay, so imagine you've got data about your house, and you want to learn how much it might cost. So you feed in the number of bedrooms, the size in square feet, whether or not you've got an outdoor tap, whether or not you've got a garage, how nice your lawn is, where the school is. You might feed in 100 different things that you think are relevant, but it might turn out that only 5 of them or 2 of them actually make a big difference. So regularisation is a bit like doing a reduction on the things that you feed in that aren't really important to the output. And there are different ways of doing that, which you can take a look at. So all of the little pictures I drew you were examples of really simple networks. So the way we count it is you don't count the input layer, you count a hidden layer and the output. So that's 2 layers in the network. And this is 4 layers because we're not counting that first layer. Deep networks might have hundreds of layers or thousands of layers. And you need that kind of complexity when you're trying to work out something as complicated as if something's a cat. And what happens is you can get some really interesting architectures. So these things I showed you were feed-forward neural networks because they're going forward. There are interesting architectures like convolutional neural networks, which try and mimic animal sight in the way that they're architected. So let's take a look at the demo. Totally the wrong link, sorry. Okay, so the way this works is you have your input here, right at the bottom, that 2 there. And that might be, say if it's 1,000 pixels, it would be 1,000 different inputs. And then the network has these different layers that try and pick out different features. So the neurons work together to work like feature detectors. And eventually you get your prediction there of 2. And this is kind of how they work. So if you imagine that you feed in 1,000 pictures of birds, you might get a group of neurons or hidden layers that learn to work out a beak. You might get a group that learn to work out the body, and you might get a group that learn to work out an eye. And what they're learning is to map these different parts to work out whether it is or is not part of something. So you might look at your friend and know it's your friend because it's his eyes, it's her nose, it's their mouth, it's their hair. And so this is trying to work in a roughly similar way that we look at things and work those out. Well, an animal does. So if you get something that's similar, like a teapot with a spout that looks suspiciously like a beak, we can see that it meets that criteria. If it doesn't meet those criteria, so it's not a bird. So once we've got past our basic neural network architectures, there's some really interesting stuff out there. So one thing is recurrent neural networks. And they work out a sequence of data, so like a time series of data. And with some of the Google Brain team, they've learned how to combine something called reinforcement learning with neural networks to make music. Okay, I'm not going to read that. So there's a lot of talk about robots taking over the world and us all becoming slaves to some kind of evil AI overlords. But the limitations of neural networks are the limitations that you'd expect from anything that's basically a complex function machine. You're not going to learn to tell the difference between a cat and a dog and then plug it into a robot and have it know how to do your job. So there's a lot of hype about neural networks, and there's a lot of really interesting research, like getting a network to predict the next series of notes in a song, or like Google Translate, like translating between one language and another. But each neural network is specialized to the task that they've been trained to. So in order to build like a really complicated human-like machine with neural networks, you might need a neural network per process. So I'm not particularly worried about the robots taking over, but that might be my own limitations when it comes to building neural networks, who knows. If you want to learn more, then I really recommend these courses. They're free, and you can do them in your own time. So if you do want to get into neural networks, please take these courses. The first one is absolutely brilliant, and it's a really good introduction to different machine learning types. The second one is a lot more maths heavy, and this is Geoffrey Hinton, who we met before. There's also now another course on Coursera from Andrew Ng, which is called Deep Learning AI, which is really good. I really recommend them. You could get really far without going to university to study them. Okay, so I kind of sped through there. Does anyone have any questions? Yes. There. That's a very big question. I can't advise you right now, and it would take a very long time. But if you look at, I think it's probably week 9 of that course, or I'll show you afterwards. I'll show you where you can learn more about it. But it's not a quick answer, I'm afraid. But I will show you after. Do you mean how the hidden units work, or do you mean the data that you put in? I think a lot of it's probably really domain specific. So the question is how to find input features, and are there any good articles about it? So far, all of the advice that I found on it is trial and error, and then data pre-processing techniques like principal component analysis, or have you heard of information gain? And using those techniques to go through the data. In terms of actually finding them, I imagine you probably need to look more towards data mining and data mining techniques. You probably find it more in that area than in the area of neural networks. I'm sorry, do you mean how do you do it without knowing about the numbers or knowing about the maths? I think it's this, I think I might be wrong that your question is similar to this question about how do you find the input features. So are you say you have a problem, you're trying to work out how to put that problem in a network, is that what you mean? Again, statistical techniques and data mining will probably really help you because it would be so specific. So it'd be really specific to the problem that you're trying to solve. So if you're trying to look at, say, predict who needs to wear glasses in the future, probably have to ask an optician. So there are probably, okay, so I said earlier there was one challenge to neural networks, there's probably two. Probably 50% of your headache is the data that you're putting in, and the other 50% of your data is tuning the network. And that's a really big challenge. And it's a really crappy answer, but the answer is kind of, it depends on the specific problem. Probably requires a lot of imagination. You'll probably find it to be a really creative process. Yes. Yeah. Yeah. It's very numeric. So all of the inputs are numeric, or like a number. But you could use numbers to represent things. So there's something called, I think they're called Hopfield nets, and it's an unsupervised learning technique, which means that you don't know what the answer should be. You just put the data in and you hope it will find a pattern for you. And what people have done in the past is they've input the entire configuration of a nuclear power plant. In a artificial neural network, then all of the inputs are numbers. But you could find a way to make something a number. So if something is on or off, you could use a 1 or a 0. Or if you're trying to put in an image, you could put in the percentage of the color that it is to represent. Yep. So you do have to numberize everything. There are examples of networks that take in character strings like letters, or sounds like sh. And there are ones that take in actual sound. But there's often processing that goes on in the background that turns it into numbers. Yes. So you're asking me that question at a Java conference, so I'm kind of torn. Well, I find it quicker to use something like Python or MATLAB or Octave, which is an open source version of MATLAB, to mock something up. It takes like no time at all, and probably about 20 lines of code to write something in Python that would probably take you about 5 cups of coffee in Java. But you can use Java libraries like Deep Learning for J, which is really good, in a Java application. I don't know about the performance difference, because the way I've been measuring it in terms of performance is how quick will it take me to write it, rather than how long will it take to run it. I was talking about this with someone earlier, but I imagine that if you took the same problem in Python and you put it in Java, it would be faster in Python because of the data structures. Because it would be faster in MATLAB. Because in Java, you don't have the same kind of matrix transformations without some serious wrapper classes around the objects. So if you want to learn machine learning, you can do it in Java, no problem. But if you want to learn how to write your own machine learning algorithms, then I would learn Python. And it's a really small cost in terms of maybe a week or 2 weeks getting your head around like Python arrays and tuples, which are horrible if you come from Java and you think, what's happening? But then as soon as you know it, it's so much faster. And there are so many, Python is such an established scientific language that there's a library for everything already, pretty much. So I would learn Python. I would say it's faster. And then if you want to write something in a big enterprise application, then I'd use Java. And I'd use a Java library like Deep Learning for J. But definitely play with Python. Anyway, it's just nice. And if you have a Mac, you can do it straight away. And I might never get invited back to a Java conference now. Hi. So it's a very interesting question, and please watch that TED Talk, because the Blue Brain project at the University of Lausanne is trying to model a human brain using artificial neural networks, which is your question, I think. And you're right in that artificial neural networks are only trained to do single things. But the brain does work in a modular way. And I have a friend who's a cognitive scientist, and he watches this. I know he's going to tell me afterwards all of the things I said wrong. But so there have been experiments that map different spots in your vision to very different locations in your brain, for example. So I don't know how they all connect together. I don't know how you would connect lots of different neural networks together to make something that resembles a brain. But I would be very interested in seeing what the project at the University of Lausanne is doing, because that's kind of what they're trying to do. And they're doing groundbreaking research on it at the moment. So if you take as a starting point that TED talk, The Brain as a Supercomputer, that might lead you on to some more interesting things that explain the answer. Hello. When you start with any network, you would probably, most of the time, randomly initialize the weights, because you're trying to learn the weights for the problem. So I'm answering your second question first, sorry. So it wouldn't make sense to train a network that can detect pictures of cats, and the output is cat or not cat, to also train it to predict the output if something's a lamppost or not a lamppost, because it's been trained for a very specific problem. So you couldn't really reuse it, because what you're training is those weights. And as soon as you reuse it, you're retraining those weights. So you're kind of erasing what you've done. But one way you could do is you could write a network that trains for those two things. So instead of having a network that trains to see a cat or not a cat, or a lamppost or not a lamppost, you could train a network that predicts the probability that something's a lamppost, or that it's a cat, or that it's a dog. So do you see what I mean? You could combine the problems into one network, rather than using network A for cats and then reusing network A for lamps. You'd have to use it for both things from the start. Otherwise, it wouldn't work. You can do that, especially with recurrent neural networks. So you're reusing the weights from one input, and you're using them in the next input, because you're trying to get it to recognize a pattern over time. So in which case, you do want it to remember states, yes. In terms of the first question, is there a relationship between the weights and is it the number of hidden layers? The simple answer is no. And I'm sure that someone will send me an email now going, apart from this specific example. But generally, if you're trying to tune your network, adding more weights is like adding more connections, because the weight really represents a connection from one unit to the next. And so if you're architecting something differently, then you would lose connections or you'd add them. So you can have neural networks, as well as moving forwards, feed back into themselves. And that would be a different type of configuration to adding more layers. So adding more layers is like letting it predict. It's a really difficult question to answer. Yep. So it would be better to add more layers because finding the weights should be done by your network as it's training. But you could change the structure of your network. So you could change where the weights are and what the connections are to build, say, a convolutional neural network where they connect neurons up in different ways and with a completely different architecture. So if you're going to add more weights, as in add more connections, you'd be solving the problem in a slightly different way. You could have something really simple, like a sine graph or a cosine graph, and you're trying to teach the network to map to it, in which case adding more layers could be the answer. But really, in terms of whether or not to add more layers or change the architecture, is part of this kind of dark art of tuning your network. And it's really specific to the problem that you're trying to solve. There is some software that tries to automate that for you. So it tries to automate the simple things like finding the learning rate and regularization, and or the number of layers. So if you were trying to solve this in reality, then I'd probably look at using one of those softwares to try and see what the best performance is with different configurations of number of layers on all of those different tuning points. And then if you still don't have good performance, then I'd look at changing architectures. And a good place to start with that is research papers. Yes. Okay, I think you're welcome. That's all I have time for. Thank you very much, everyone. Thanks for coming to my talk.